Right, yeah, thanks very much. So I've reorganized my plans a little bit, given that I now better understand what the interest is among several participants, particularly among the organizers. So what I want to speak about now is actually I shift gears, talk about physics, actual physics now. And I want to present an actual physical system, these topological materials, these fractional quantum Hall systems, and their quantum observables and how they fit into the scheme that we've been discussing. And then maybe tomorrow we talk a bit about how to figure out how to make measurements, what it actually means at quantum measurements, which is, I think, not actually a well understood question. People like to speak about how eventually these things are going to be used for quantum computing, but there's, I think, a fundamental question of how to actually go about it. So what I'm speaking about now is actually following this article, which are lecture notes that I just made recently for a different event, engineering of anions on M5 brains. But don't worry about the terminology. We'll just look at some concrete things, and you'll see the formalism maybe in action. So before we get to that, I talk a bit about group points now. I understand there's a considerable interest, especially among the organizers, in how this formalism generalizes to group points. And so what I'm speaking about now here, let me jump ahead, is discussed in much more detail in this article, Entanglement of Sections, that we wrote, which effectively gives a model category structure on these dependent quantum data types that are discussed, but in the fully infinitized version, where the base spaces are infinity group points, modeled as simplicial group points, and where the vector spaces are generalized to chain complexes modeling HR module spectra. So we'll just need a super tiny aspect of this big article. It's a technical article constructing the model structure, not just the model structure, but making the external tensor product, so the quantum entanglement, that's why entanglement is important, making that into a derived functor. That took some work, but that shall not concern us here, just so that in case you want to see more details, it's in the article, Entanglement of Sections. So I'm experimenting a bit with this new way of presenting things. Let's see if this works. So we keep zooming in onto stuff. So the categorical formulation that I've been describing, where everything was, the model we've been discussed was super elementary, was just sets with the vector bundles over it. But the way I tried to present it was such that we brought out its abstract features, like there were these adjoint triples of base change junctions in particular. And such adjoint triples occur in broadly more general context. And our main conclusions, for instance, crucially the monads that we discussed, right? We found that from such an adjoint triple, from these base change adjoint triples are induced monads, one of which actually controls the concept of quantum measurement, including all the subtleties of the collapse of the wave function. And we saw that once you formalize quantum measurement as being that co-monad, very somewhat less obvious aspects of quantum measurement, like the deferred measurement principle, actually are provable consequences. And in proving that, I was very brief on this point yesterday, but I amplified that it was just using the Kleisli equivalence, just abstract nonsense. So the same proof actually works in broad generality whenever we find any other data that kind of organizes into these adjoint triples, so that forms what in type theory we might want to call dependent linear types of sorts. And the first generalization of among a large tower of them is where we promote our base sets to homotopy one types. So let me, since I gather we're not experts, everybody here on homotopy theory, let me speak a bit about jargon here. So there's a field, of course, called homotopy theory, where people originally at least talked about spaces, and these days, or then in the last decades, people shifted attention from topological spaces to simplicial sets mostly. These days, people talk about infinity categories and mixtures of these concepts. So in homotopy theory jargon, what's called homotopy one type is sort of a topological space whose homotopy groups are concentrated in degrees 1 and lower. So in category theory jargon, these are one group points or categories where all the morphisms are invertible. But so the physics style meaning, which I maybe want to amplify because there's all this jargon here, right? And you might think maybe it doesn't concern you. But what it really does is it's talking about sets where gauge symmetries are kind of built in. Elements of the sets may be gauge equivalent to other things by specified gauge transformations. And another piece of jargon I want to get out of the way, you may have noticed this before, but I don't know if it's it's rarely made very explicit, is that there's two different conventions about jargon in physics and in math. So there's a whole lot of things in physics that are called topological. Here's the examples: topological quantum field theory, topological phases of matter, and then of course the topological quantum computing that I've been talking about. And people like to say topological, and the mathematician might say, okay, they're probably interested in homomorphism types of topological space. That is not the case. So that topological is a bit of an abuse of terminology. What one typically means in physics when one adds the adjective topological is really what in mathematics is called homotopical. So homotopical, at least in the original construction, it does involve topological spaces, yes, but it takes them just as a model for something coarser, namely for their homotopy types. So in homotopy theory, one considers topological spaces up to what is called homotopy equivalence, and I'll recall what this means for the group word case in just a moment. And hence it's just representing the homotopy type. So very different. So spaces that are far from being homomorphic will be considered as the same. In homotopy theory, if only sort of there's a map between them that identifies their homotopy groups. So the homotopy groups serve kind of as a fingerprint for these homotopy types. So this is just as a caveat so that you can orient yourself in the terminology. And I'm going to say now what homotopy equivalence actually means, but I do it right away in the model of group points. So, right, as I already made this little joke last time, in all these lectures, I think several speakers, not just me, had this problem. We introduce these concepts as if you don't know them, and then a minute later we use them as if you do know them. So, of course, we've been talking about categories all along, and group points are just special categories. So we should be really assuming we know all these things. But it's actually another maybe little appreciated fact that even though you can understand group points as being special categories, the theory of group points is kind of different from the theory of categories. The theory of, in a profound sense, actually, the theory of group points is the beginning of homotopy theory. And the theory of categories is something like directed homotopy. So it's actually worthwhile looking at group points in their own right for a second, even though they are special categories, and we'll make use of it. But the idea of a group point is, as I said, you should, for what follows, since we've been talking about sets of measurement outcomes, I want to advertise thinking of them as being sets of gauge transformations. So group points, it's a really simple concept. It's not in itself really kindergarten stuff. But anyway, it's like, so think of sets with gauge transformations. Gauge transforce, eh? So the idea being that, naive version of a set where you have points, say S1, S2, S3, or maybe I should call them W, these were our possible worlds. So now we allow for the fact that maybe there's two possible worlds here, or too many worlds, where some of them actually are nominally different, and yet some are the same. So we say, well, there may be gauge transformations between them, which are generally called gamma. This will be a world, if you will. This will be some sort of gauge transformation, by which I just mean in the broad sense. So this might be, and it will be in what we consider in a moment, these worlds might actually be configuration of gauge fields. These will be actual gauge transformations, but you can think about it more generally. Anything, gauge transformation, like not necessarily in gauge theory, but in any theory of symmetries that are sort of not meant to be observable, but that are there. And then, right, so you have these arrows in there, and there may be different arrows between, there may be different gauge transformations between the same things. There may be no gauge transformations between some things there, and so forth. And these things, these gauge transformations are meant to be invertible with respect to some units of the composition. So that's the point that they are all invertible. So that's what makes it a group point. In particular, if you have a single object, then the auto gauge transformations, they form a group under composition. Form a group. So that's where the word group point comes from. It's like a group that has not just a single world that it's acting on. It's not just transformations of a single thing, but it can transform between. Okay, maybe I'm too elementary now. So that's group points. And maybe let me introduce the main characters that we'll meet. The key examples of group points, for our purpose at least, are gonna make right here. The main example we'll need maybe at the end of the 90 minutes today is the fundamental group point of a space. groupoid of a space, of topological space, which you've all seen, but so X is a topological space, and then the elements, which jargon calls them objects, so the elements of the set on which we have gauge transformation, objects are the points in X in the underlying set, points of X, and the gauge transformations, now called morphisms, this is the jargon here, morphisms are, so say, it's homotopy classes of paths. Homotopy classes of paths, continuous path classes of continuous paths. Yeah, I saved on the slide, maybe it's okay. Relative to the endpoints. So if here's a point X and here's a point Y, and here's a continuous path, then we can continuously deform it into another path, then we regard them as the same morphism in the fundamental groupoid. Whereas, they cannot be transformed, then this will be the point of it. If the space has some hole here, there's some topology, then they will represent different elements in the fundamental groupoid. Another important example is the quotient groupoid. If we have a group G acting on a set S, then you can form the corresponding homotopy quotient or quotient groupoid whose elements are the elements of S, and where if a group element G turns an element S into its image under the group action G of S, then we regard that with that label of which group element is doing this into a morphism. And again, on a composition of group operations, this is clearly a social difference, such forth. This is the one that is of interest to us. Gets an extra name, the looping groupoid, even though it's a special case of the action groupoid. Any group acts trivially on the point with trivial action. The whole point is to not pass to the plane quotient. You see this homotopy quotient here is called the homotopy quotient because it retains more information even if the action has fixed points. Even if G of S happens to be S, since we label that morphism, we remember which gauge transformation took S to itself. We remember the actual gauge transformation as opposed to just the gauge equivalence class. That's kind of the point of groupoids, to remember gauge transformations. And in the extreme case, we have this situation with the group just entirely there's just a single world, if you wish, and the group just has no other means instead of acting trivially on it. But still we get a groupoid, we have still the group of all these gauge transformations on this thing, which we don't otherwise know. And it goes by the name BG because for reasons, because the geometric organization, something else one can do with these groups, or rather I should say the topological organization of this thing is a space, which is the space that since the 1940s goes by the name BG and is the classifying space for group G. And we'll see more classifying spaces just in a moment. This is kind of the groupoid origin, the groupoid avatar of these. So these are the groupoids we'll be playing with. And then, so I just want to be getting at the notion of homotopy equivalence. So a map of groupoids is of course a functor. I guess I shouldn't be too elementary. Let's just assume we understand what this is, right? So we have two groupoids. Then mapping one to the other means you map all the set elements, all the objects to each other, and same for the gauge transformations, such that the composition is respected. The identities are respected. And so then a homotopy between two such maps, here called F0 and F1, denoted suggestively like this, is the analog of a continuous deformation. If these were maps between topological spaces, in fact, that's exactly what it corresponds to under if our G's are fundamental points of spaces. It's kind of a deformation now object-wise. So here's the image. Here's one morphism in our domain groupoid. Here's its image on F0, its image on F1, and we ask that we have specified transformations at all these points, if you will, morphisms in here, such that these diagrams commute. So continuous deformations at this more discretized groupoid level. And the important point then is that we can, using this, speak about. So the idea is that the homotopies are kind of the gauge transformation of the groupoids themselves, right? So we started out with saying that groupoids are like sets equipped with gauge transformations, but then groupoids themselves form such a structure. There is maps between groupoids, and we want to be talking about gauge transformations between these maps, if you wish. So I'm giving an impression of how groupoids are enriched over itself. Anyway, so we can now say, well, let's now, since everything is supposed to be up to gauge transformation, since also understand groupoids, their identification only up to gauge transformation. So instead of speaking about two groupoids being the same, so having isomorphic sets of objects and morphisms, we want to say, well, no, maybe something weaker can happen. Suppose you have two groupoids G and H here, and then we say gauge equivalence is a map such that there's a map F here of the form we just introduced, such that there's a map going in the other direction, which is an inverse up to gauge equivalence, so that we have homotopies like here. So if you go with F from G to H and then with F bar back, it need not necessarily be the identity on G, but there needs to be a homotopy. It needs to be the identity of the homotopy and conversely. And right, so the slightly, I call it a theorem here, of course this is a lemma or an exercise, not even that. But the fact that we're going to use, which is important in this kind of business, is that you can easily check now that any groupoid is actually homotopy equivalent to the disjoint union of the looping groupoids of the fundamental groups of the connected components. Right. So I should say first, I promise actually to say this for let's do it now. So of course we have now this terminology of homotopy groups. We know from topology, but it has now a direct incarnation, of course, in groupoids. We say pi 0 of a groupoid is just the equivalence classes of its objects under its gauge transformation, so the connected components. And if we have an object of a groupoid, of course, pi 1 is, as I already denoted here, is the group of its auto gauge transformations. That's the fundamental group of the groupoid at that point. And these two lines are meant to indicate that this is compatible with the notion in topology, if you care about that. So this is the connected components of topological space, end up being, of course, the connected components of its fundamental groupoid, and similarly for pi 1. Okay, so this pi 1 back. So we have a typo here. Pi 1.
So it's the connected components of the homotopy groupoid of the space X.
Oh, it is a silly typo, yeah. Sorry.
That's fine.
Sorry, this is an X. Yeah, I ran into some time issues actually with preparing this. So this, I'll fix this. I'll fix it on the website. Sorry, this is okay. Right, pi 0 of X, you can first turn X. That's a stupid bad type. Turn X into a groupoid by applying pi 1, and then apply pi 0. Thanks. Yeah. Sorry. Right. So then, right, we can do the following now. So we have all these connected components of a groupoid, and in each connected component, choose one representative of the points there, one gauge representative, and it has a pi 1 of auto gauge transformations, and of that we can form the one object groupoid. And then form the disjoint union. So I didn't introduce disjoint unions of groupoids before, but it's the obvious thing. If we have one groupoid and another groupoid, then just putting them next to each other, you get another groupoid, right? With the union of objects and the morphisms between them as before. And any groupoid is actually equivalent. You can decompose it like this. This uses, if you want to be pedantic, uses the axiom of choice. So if your groupoid has the non-finite sets, then there's but that's what you assume. And okay, so then we're going to be talking about linear representations, and I understand that's of particular interest here. So yeah, maybe I should, let's go here. So a linear representation of a groupoid, now we want to be speaking, so a groupoid, I said, is like a generalization of a group. A group has linear representations. What's the generalization now of representation of groupoids? So here's, this is maybe a bit idiosyncratic what I did here. I just wanted to phrase it now all in the category of groupoids. So I'm saying, I'm speaking about the core groupoid here. Let me write core of mod C. Remember, mod C was my notation for the category of complex vector spaces. Just so that it lives now in the world of groupoids, I say core of it for the groupoid whose objects are the complex vector spaces, and whose morphisms are just all the invertible linear maps in it. So every category has a groupoid core, just the largest groupoid inside it. You throw away all the non-invertible morphisms. I'm not sure if that was a good decision here. Of course, you know, a groupoid mapped to a core is not equivalent just a functor from the groupoid regarded as category to the ordinary category by the fact that we have this inclusion in quotation marks. The groupoid core sits inside. Anyway, so let's just so a groupoid representation is just as you would hope it is. It on complex vector spaces for us. So just assigns to every object to every world the corresponding vector space, a quantum datum. Right, so G goes to say core. We can omit the core, whatever. Mod C. right? Then here it has an element S1, so S1 goes to some vector space. We maybe call it H to be suggestive, HS1, kind of the quantum states at that world, but there may be another world here, HS2, but then there's a morphism here, gamma, or if there's a morphism here, you'll assign a corresponding linear map here, rho of gamma or whatever, rho of gamma. An isomorphism, in fact, because we're going to the core. And such that this respects composition. So if we go to S3 with the gamma prime here, then we have, of course, gamma is composed like this, or a gamma prime, and it has to respect composition. Rho of gamma prime. And we want that the composite here is the representation of gamma prime. So you can see immediately that if there is just a single object, or actually if you just restrict attention to any one single object and take all these gammas to go from S1 to S1, then this is just a representation of the automorphism group of the S1, but in general it also knows how to connect these things. So that's a groupoid representation, just a functor.
So you're going to consider just as algebraic, pure algebraic level, not topology.
Yeah, I'm not considering topology here. Yes. Exactly, yeah. Yes. And so then what in ordinary representation theory would call an intertwiner between two representations, or homomorphism of representation, is not just a homotopy between these. So an intertwiner of groupoid representation is just a homotopy between these groupoid maps. That was my reason for introducing this core thing, so now we can just speak about homotopy. So two representations may be essentially the same, maybe gauge equivalent, if there's some homotopy between them, and that gives us the category, in fact, the way I phrase it out, a groupoid of G representations. Yeah, maybe actually I shouldn't. This is actually not good the way I'm writing it. Yeah, I should fix that. We want to allow this to be any natural transformation that is not necessarily invertible. So these are the invertible transformations, and the category we would like to allow non-invertible ones. So there's a category mod G, which so as the notation is meant to suggest, this is to remind us of the categories where previously we had in the previous sessions we were talking about mod C W here, where this was the W indexed sets of vector spaces. The set of worlds is now replaced by a groupoid. And an important remark, for example, in this business is what happens to the this is the question. What happens to the representations of these fundamental groupoids? It's a basic fact of whatever differential topology that the representations of a fundamental groupoid of a topological space X are equivalently vector bundles. So how does this come about? Roughly, I mean, here one does have at an intermediate stage think about the topology a bit, but it drops out in the end again. So to each object in the groupoid, we're supposed to assign a vector space. So that gives us a vector bundle, if we're careful with the topology, because the objects of the groupoid are just all the points in X. So we get a vector bundle over X, but then that vector bundle also knows that its fibers are identified for every path in the base in such a way that these identifications don't depend on the homotopy classes of the paths. And that is exactly what a flat connection on a vector bundle gives you. It assigns, well, a connection, first of all, assigns to every path, every smooth path, first of all, an identification of the corresponding fibers. And then if it's flat, this assignment is independent on a relative homotopy of paths. And so what we obtain here is now by representation of the fundamental groupoid, or generally by groupoid representation, is that we obtain dependent quantum data as before, and that these vector spaces that are involved in the groupoid representation depend on the objects in the groupoid. But now this includes operator actions for every path in the groupoid, or every actual path, every morphism in the groupoid, or actually the actual path in the space. We get an operator, a linear operator acting on these quantum data. And so this is how, maybe this goes a bit, maybe I should have mentioned something like this yesterday when there was a question about quantum systems, right? Maybe that was you. Or, okay. So this goes, this equips our bare quantum states with a bit more structure. And now we observe, this is the key observation, that group-wise representations again they again behave like dependent linear types do. They have base change in joint triples. So first of all, in a simple way, if we have a map of groupoids from G to H, then we get an evident, this is not a typo here. Yeah, you can see I was running out of time. This is mode, this G has to go. This is mode H. So we can just precompose, right? If we have an H representation that was just a map from H to core of mod C, we can precompose it with a map that we just assume to have from G to H, and we evidently get a morphism representation of G now. So that's called the pullback or the restricted representation. And one can now see from abstract nonsense that these pullback functors have left and right adjoints again. This comes from Kahn extensions since mod C is complete and co-complete. These things exist. There's formulas for them, Cohen formulas, which are actually obtained if you click on Kahn extension here, which I maybe don't do right now, but we could if we wanted to. Maybe it's more useful to say what it comes down to in the case that we kind of reduce back to ordinary groups. So suppose we have a subgroup inclusion G into H, and we regard it now, turn it into a map of groupoids. So regard our F here as being map BI. So the induced map from the delooping groupwood of G to the delooping groupwood of H. This is just fancy notation for saying we'll just apply I on the morphisms, right? This is a single object, this is a single object. The morphisms here form the group G, the morphisms here form the group H. And so we get this functor. And so then you can ask, well, what does this abstract diagram that I just claimed here without really explaining it, what does it do now? And it turns out it produces the left adjoint and the right adjoint functors produce the canonical standard notion of sort of left and right induced group representations or induced and co-induced representations. So concretely here, as you can see, there's formulas for this. The left induced, which is mostly what, like when you look on Wikipedia or something, they will actually define this left functor. You take suppose you have a G representation, you can sort of tensor it over G with a permutation representation of H, and then this thing then has an action of H. So this is classical business. This is Frobenius reciprocity theory. That's the big name for what this means. And if you want an even bigger name, I'm quite fond of this, but maybe we shouldn't talk about it too much. There's more structure here. These are tensor products. This functor is actually strong monoidal closed, this functor, and together, these three functors, together with the tensor and the internal homie, make 5 functors, which are really a shadow of 6 functors because there's 2 of them are secretly identified. So an even more grandiose name for what's going on here is Grothendieck's motivic yoga of 6 operations. It's really behind these constructions as one goes now through. I think this is, I'm fond of this because I think the notion of motive that Grothendieck was originally after, it's actually to do with quantization. It's turning a space that's converged, but that's not important. So I'm calling it here effect. This number 6 is again this article that I mentioned, entanglement of sections where these things are built. But in any case, we can again form the Grothendieck constructions of these groupoid representations, which without maybe saying it in detail is just this is easily understood in this picture. If I could only find it, where was it here? You should think of these groupoid representations, or at least sometimes, often it's useful to think of them as being vector bundles, flat vector bundles over a space, and as such, there's an evident notion of morphisms of these things where the base may change. So if the base is fixed, you can have a morphism of vector bundles that respects the flat connection. But you can also, as we had last time, we had these diagrams where X may go to Y, and then the corresponding linear maps of fibers cover that base. Actually, that's really exactly what is going on when you do this Grothendieck construction. So there's a direct extension of everything we discussed in the last 2 days, where we're just down in the base, we have these gauge transformations. All right, so just to conclude this, but no, that was the conclusion. So,
sorry,
yes.
How is this different? I missed the end of yesterday's session, but if X is just a set, not a groupoid,
Right.
it's still a vector bundle just over a set, so we don't have
Yes.
isomorphism between the
Yeah, thanks for asking this. I should have, of course, mentioned this. Of course, I talked about how groups are kind of, one has to be slightly careful with the base point here. Groups are kind of among groupoids, but of course, sets are too. I should have amplified this. It kind of unifies sets of group with groups. So, of course, you can erase that, no problem. You use, sure. No, nobody knows what it is. Right, so category of groupoids. There are sets in there, actually, it's a full subcategory. It's just the groupoids without any gauge transformations. So everything, so this what we're doing here is a strict generalization of everything we did before. Everything we did before is still in there, but it generalizes. Then groups have this functor B to there. Just be a little bit careful. People sometimes say, or some famous people put this meme around, but it's not quite right, that groups are the same thing as groupoids with one object. Is not quite true. They're the same thing as pointed groupoids with one object. But okay, that's not. Okay, so that was the lightning version of how to generalize everything I said before, this whole quantum yoga to groupoids. And one can go further now. Now you can do the same thing with simplicial groupoids and the chain complexes of vector spaces. But what I want to do now is I entirely switch gears now for something that, first of all, that for maybe 30 minutes now may look like something completely different. We're doing physics now, or some algebraic topology version of physics. And then we see how we actually produce interesting examples of these things, non-contrived, that sort of really appear and that are of interest. So I want to apply stuff now to these infamous fractional quantum Hall systems. And I should warn you, I'll point in the lecture notes, I point to standard sources on fractional quantum Hall systems, but what I'm presenting now is an idiosyncratic new way of thinking about them. But this is now from this engineering of onions on M5 brains. And let's just see what we want to do. So we're now interested in the situation where we're actually in the lab and we have maybe some slab of semiconducting material at very low temperature, and we're turning on a huge magnetic field or very large magnetic field transversely through that thing, and then see what we observe. And before I say what one actually observes, let me start by saying what one would naively expect, or naively in quotation marks, because this uses a theorem which is just proven recently. But the whole point will be of these topological systems, these topological quantum materials, the point is always that they're strongly coupled so that from the actual microscopic degrees of freedom, the usual electrons, it's hard to impossible to actually deduce what the system is actually behaving like. There's always some kind of transformation going on where, since the electrons couple so strongly to each other, they effectively form a new kind of thing called a quasi-particle. And these quasi-particles obey laws that may be roughly like those of electrons, but in detail may differ. And so we'll start by looking at what sort of an actual, maybe free electron would see and feel. And then we see how to change things to account for these topological physical effects. So we're going back maybe 200 years to the 1850s when Faraday was making his experiments in understanding magnetic flux. I'm just saying this because once I gave a talk on flux, at the very end I realized that nobody in my audience knew what flux actually means. So I'm just saying it in case it just, if you know it, just let me say it again anyway. So remember, back then in the 1850s, they made this startling observation. Faraday had these rod magnets, or horseshoe magnets, and put a sheet of paper over them and strew iron filing over that. And then one observes that the iron filings align in what the eye perceives as being lines that seem to emanate from the poles of this magnet or converge back to the poles. And so if you have some surface here that's to be indicated here, we can be talking about these magnetic flux lines as they came to be called, penetrating the surface. It's called magnetic flux. It's the magnetic field lines. It's some indication of that there is something going on there, which is now called a magnetic field, which you can't really touch, but it's there. And as the picture is meant to suggest in modern language, even though that doesn't actually play much of a role in what I'm going to say now, but you measure the magnetic flux by saying, well, okay, let me define what the flux density is, or how much flux there is through any tiny little surface. And they eventually define a two-form called the Faraday tensor, which, if evaluated on a tiny surface, tells you how many flux lines go through. So that's a measure for the magnetic flux. And and maybe I can, I don't know, at this point, let me actually say something. Where's better on the board to read for everybody? If I write on the left or on the right? It doesn't make a difference. Let me write here. So I need to, since I just spoke about the 1850s, let's maybe spend 5 minutes just on recording something that may not be completely widely known. So in 1850 and in the coming 80 years, people thought that the electric field is therefore given by, so this is my notation, omega de Rham for smooth differential forms. You see we're switching gears now, this is some different topic. So suppose this is our space-time here, space-time manifold, the world we live in, and we're looking at closed differential forms in there. And the object we are interested in, as I just mentioned, is called the Faraday tensor. So it encodes the electric and the magnetic field. If we're on Minkowski space-time, so if we have canonical coordinates x1, x2, x3 for space and t for time, and this thing is the true form whose temporal components are the components of the electric field, the way you learned it in school. So to some science that I will mess up now. The x1, the xt component is the coefficient, is the electric field in x direction, and similarly for E2, the x2 for HDT is the component, similar for E3, blah, blah, blah. And then so this is all the time component here, and the purely spatial components of this two form on, say, Minkowski space-time for a second, are the magnetic field. So there's the magnetic field component V1, and it's the coefficient of dx2. Can you read this? Right, dx3 plus cyclic permutation. So the important point is just the electric field and the magnetic field are canonically components of a single two form, the Faraday tensor, which is a smooth differential form. And then half of the Maxwell equations, one half of the Maxwell equations, the Gauss laws, say that in modern language that if this form is actually closed. The other half says that also this Hodge-Rule is closed, which is important, but I will ignore it here for reasons that I can explain. I should and can ignore it. If you're worried about this, let's talk about this later. And then, right before I come to this, and to the story on the board here, I want to just say, so for many decades to come, people thought that this is the description of the electromagnetic field, the full description. And then Dirac came along, quantum mechanics was invented, Dirac came along, and he made some argument, which in modern language, that's absolutely not how he said it, but it's absolutely what he actually did. Like if you just translate language, what he actually did argue, in hindsight, he observed that there's actually more information, which is now called the gauge potential. But the way it comes about is that one says, well, actually, in addition to just these differential forms, which represent classes, of course, in the Rham cohomology of X, right? The equivalence classes under adding exact forms with something called the Rham cohomology, which is of course isomorphic on a suitably nice space, which our manifolds certainly are, to the real cohomology of our space. So the argument was, Dirac's argument was essentially that this real class that underlies electric field cannot actually be arbitrary, must actually be in the image of an integral class. So there's also cohomology of X. So this is like singular cohomology or Czech cohomology, whatever way you like to compute ordinary cohomology groups, cellular cohomology. So there's cohomology of coefficients in the integers, and there's a canonical map here, which at the level of just these groups, you can think of as being just the inclusion of coefficients here, single scalars. Any Z cocycle, Z value cocycle, certainly an R value cocycle, you can map that here. And then the observation, the idea was, and I write on, the idea was that the full electromagnetic field is this two form plus some datum that actually controls an integral class such that they are actually compatible here. So in modern language, we say that the full electromagnetic field, and the notation is people like to put a check on here, but I don't want to do that, because Czech cohomology does exist. So let me call it diff for differential cohomology. So there's another group one can put here, which has projection maps out. For any element in here, you find a closed differential form from that element, and you find, let me call this chi maybe for class. You find an integral class, such that they make this diagram commute. So the most prominent, the most popular realization of this is as complex line bundles with connection, and isomorphism of these with connection modulo isomorphism of these things. That's one realization of this thing called the differential cohomology. Diff cohomology. Differential cohomology of X. And now,
Is this where Chern classes live? Or not quite?
so Chern classes are related to this. Chern classes sit in here, but well, the first Chern class lives in here. So if you regard this complex line bundle as a unitary bundle more generally, it has one non-trivial Chern class. The first one, this chi is C1. So, okay, I mean that's a long story. So now maybe seeing this diagram, you should. So and the connection here, of course, this is the gauge potential, right? This is what in physics is called the gauge potential. So this is the extra ingredient which refines the whole picture. But now we want to maybe, since we're about, as I just indicated, about to see that maybe this situation gets modified if we have topological systems where we're talking about effective fluxes. It's worth thinking about what this maybe means more generally. And the first thing you should ask when you see a commuting diagram like this completing a cospan is it a pullback? Is it like uniquely defined? And it's not a pullback, but it wants to be a pullback. And the reason it's not is just because we're working on cohomology classes, gauge equivalence classes, in a theory that is inherently a gauge theory. We should not, to understand what this thing really is, we should not pass to cohomology right away. And now comes the step, which is kind of well-known in algebraic topology, but I don't know how widely that has. Or does it? I don't know. Does it work if I just write here? Can you see? You can't see that, right?
Not from this side.
You can maybe use this side of the board now.
Or I go to the other. Well, I want to complete the diagram. Maybe if I just go like if I just put it like this for a second, can you see? I mean, it should be possible, right? This should work. So there's a basic fact from it must be in the 1940s or earlier that integral cohomology has classifying space. So I'm going to be talking about classifying spaces a whole lot. There's a space here which carries some name. Actually, a good name for it is B2Z, but that's not how it's traditionally called. Traditionally, it's called. I mean, it's just crazy. Crazy too. You see, apparently the information about this space is in the fact that there's integers in degree 2. It's called an Einberg-MacLane space. It's also homotopy equivalent to BU1, and if you like, it's also represented by CP infinity. So it has lots of names, but it's anyway. It's characterized by the fact that it's only non-trivial homotopy groups are in degree 2, and it's connected. And there the homotopy group is Z. That's what it says. And one can show that is the non-trivial statement that actually characterizes a space uniquely up to homotopy equivalence. And so it turns out that the cohomology is actually the connected component of the maps from X to B to Z. We can form a mapping space. The space, the elements are all the continuous maps from X to this BZ, which is kind of the co-cycles now, which we didn't see here. And then we take, so this space carries a topology called the compact open topology. So it's again a topological space. And of that space, we can take pi 0, which means take the homotopy classes of these maps. So what we're saying here is that this what is traditionally constructed maybe using singular cohomology or check cohomology, where you build chain complexes in order to then pass eventually the chain cohomology of a complex. There's another inclination, which is actually more profound, which doesn't quite go to chain complexes, but it still has a sort of co-cycles, like elements and co-boundaries between them. A map is like a co-cycle, and a homotopy between two maps is like a co-boundary, and passing to the homotopy classes is going like the passing to the cohomology. And so what this diagram really wants to be is it really wants to be understood before taking pi 0 here. This is the step that goes to gauge equivalence classes, which destroys a whole lot of information. And there's a similar space here, so the situation continues down here. There's a space called B2R. right? And which is defined the same way. It's only non-trivial model group is in degree 2, and where it's R, and forming maps into that. I'm writing unreadably now, but maybe you can handle it. And these spaces here, these spaces have maps to each other. And the corresponding map is just the one induced from this. And so in the full story, I'll stop here though, but this is a whole lecture in itself. But in the full story, you replace these things by classifying spaces, or this guy here. We have some, for instance, if we were classifying RR fields in string theory or something, we would choose a very different classifying space here that classifying complex K theory. And in general, if you have any gauge field, any high gauge field, so there's some classifying spaces here that are admissible flux quantization laws, as one says. Because the quantization refers to the fact that we're restricting the total flux to be some integers, something. So in general, we have some space here, some classifying space, which I'm going to call A. And it has what's called a character rationalization map that gives kind of an approximation of that space in some non-abelian form of real cohomology. The differential forms, and this is the subtle part, will map to this in a context where differential forms live alongside spaces. That context is called Topos theory. So I'm not going to talk about this now, but you can make sense of this. And then you form what's called the homotopy pullback of this situation. That will give the thing over there, correct? So the upshot of this story is just that we want to be thinking of flux quantization laws, like globalized definitions of gauge fields that take into account not just the local fluxes, but also some global constraints by choosing classifying space. And the classifying space for ordinary electromagnetism is B2Z or BU1, as we're going to call it. And now let's first look at a standard, not a standard. So here's a little theorem which I'm just going to throw at you. This is proven. So part of this theorem was known for a long time, but a lot of it wasn't known. So this is proven in this article here, Quantum Observables of Quantized Fluxes, which we published a while back. It's a straightforward computation, but it appears to be that this hasn't been really stated before, and it has consequential implications for what we're doing here. So the theorem says now the following. This actually holds for general gauge groups G, which are why I'm writing this in this generality. But for us, let's just take G to be U1. So wherever G appears, just think of U1. And so we can ask now the following thing. Suppose we have a spacetime of this form here, where we have a surface, and that surface is going to be this chunk of semiconducting material. That's what we want to think of that we have in our laboratory, or some effective form of it. And the rest being Minkowski spacetime, R11. So this is the situation we may actually have in a laboratory. And there's flux, like magnetic flux now through this surface. And we want to know is what is now the quantum observables on this flux. Like we talked a bit about what the flux is classically, but now we want to ask, well, okay, what are the quantum observables? The quantum observables, as you know, they should. Now I'm talking about observables for a second. We'll come back to states in a moment. We haven't talked much, or I haven't talked much about observables at all so far. But at this point, we want to be speaking about observables. As you know, observables form a C star algebra. That's kind of the definition of what it should be. Possibly non-commutative. That's the quantum aspect. C star algebra. And now we can ask, well, what is that C star algebra of observables just of the flux? So it's an unusual question, which is why I think it hasn't found so much attention. Usually, people ask for the quantization of the full theory of the gauge potential. Then there's a whole big story about how to, there's quantization of that. I'm asking the question here, and we're kind of in the process of zooming in into just these topological fluxes that we understand. I'm asking, what is just the quantum observables on just the fluxes? So there's one article by Siegel, Moore, and Fried where they address it. There's a couple of articles in that. I think it's called Uncertainty of Fluxes, where they ask this question: what actually are the quantum observables on just the fluxes? They have some arguments, but this is a theorem here, which follows by just writing out. You write out the phase space for Yang-Mills theory. In this case, you look at the commutators of Poisson brackets between the fluxes, not between the gauge potential and but just between the fluxes. You find that these commutators actually form the Lie-Poisson structure, or this commutator address the Lie-Poisson structure of a certain group, and leap for some phase spaces actually have non-perturbative quantization. So I'm just throwing around some terms here. So there's something called non-perturbative deformation quantization or refill quantization. And if you open just the standard textbooks on this, what it does to our situation, this is the following answer. So just try to indicate roughly how this theorem comes about, but here's what it says. So this C is innocent notation for complex C-star convolution algebra. So let's first think of it. This is here a group, a topological group, in fact, a Frechet-Lie group of what? Of maps. This is our surface, sigma. We assume it to be a smooth manifold, as we should. And this is first of all, the set of smooth maps to our group. And there's actually some choice here. We have in this conversation process, at some point you have to choose a lattice inside G, which is ad invariant with respect to the joint action of G on its Lie algebra. In any case, then there's this semi-direct product group here, which plays the role of classifying the magnetic, in the proof, I can see this turns out as classifying the magnetic fluxes. These are the corresponding electric fluxes. If you're really dealing with U1, then this is U1. The lattice can be chosen with the integers inside R. So this is another copy of U1. And so you just have the kind of duality symmetric flux quantization of electromagnetism with U1 and U1. Anyway, so it's this group. This actually forms, as long as this is compact, this actually has the structure of an infinite dimensional manifold with Frechet smooth structure. In any case, it's a topological space. And of that, we can form the convolution algebra of compactly supported complex functions. So it's a bit of a mouthful. I'll cook it down in just a moment to something actually simpler because we're just interested in the topological aspect of it.
The commutation, the commutation structure is in the convolution algebra.
Yes, yeah. So this is a non-commutative algebra due to the because this is and so right. So this is just the answer. So this just to bring. So a lot of physics is now encoded in certain algebras. But now, for the purposes of I'm getting back to my motivation section here, where we said, well, we want to make use of such quantum observables now for actual manipulations that can be useful for maybe quantum computing. And so the idea there is, as I mentioned on the first day, is that we want to be looking at the robust observables, those that are not affected by local fluctuations, those that are insensitive and will not decohere due to local noise. And a very easy way to understand what we have to do now in this formalism is that clearly we don't want our observables to depend on what exactly the fluxes do at every point. What we really want to do, we want to get some global impression of what is the total flux for some meaning of total through our surface. And what some meaning of total should mean is really easy to see. Let's just look at the observables that really just depend on which connected component in the group you are. So we just put a pi0 here and pull back our observables. So these are the robust topological observers. They can just see in which connected component we are, which precisely means that all continuous deformations of the flux, which is sort of where noise lives, are being ignored. The observables here are exactly those that give that make the same observation on a configuration and its noisy version. So that's exactly what we're after. So it includes here. And then the next proposition is also from our article, but this proposition is now a really standard exercise in algebraic topology. I can maybe indicate how it goes. So it shows how this subalgebra now, which I'm going to call the topological quantum observables, can be reformulated just a little bit. Let me just indicate how such a proof goes. So I'm ignoring this piece now just for simplicity of notation, which is the case that lambda is 0. If you take lambda to be the 0 lattice here, then you have this factor of G here, which smoothly plays a role, but topologically it's contractible, so on pi0 it no longer contributes. So it's not the full case, but it's good enough for purposes. And then we just have G here, just to simplify notation. So what we're doing now is our convolution algebra now, since this is now a discrete group, it has no longer topology on it. So we've just thrown away all the analysis involved in making sense of a C-star convolution algebra of a topological group. It's now the actual naive convolution algebra of a discrete group. The discrete group is the connected components of maps from sigma 2 to G, but by a standard effect, which I like to call it somewhat a smooth Oka principle, like homotopy class of such smooth maps, actually the same thing as homotopy classes of continuous maps. There is some basic fact of algebraic topology. We can just, in order to compute this thing, we can just as well use continuous maps, which is useful because then you can use more results from algebraic topology. So pi0 of maps into a group is actually the same thing as pi1 of maps into the corresponding classifying space. This is why on the previous slide, actually I called these classes this B, I called it de-looping. That's exactly where it comes from. Kind of, if you look at loops in this space, which is what pi1 is of course doing, you just see G. So it, right, loops of BG is G in this sense. B is de-looped G. That's where the terminology comes from. I'm reformulating it here in even different ways, which is important for some things, but actually for our purposes, we can stop here. This is the incarnation of the observables, the topological observables that we'll be dealing with. And just notice the form it has. It says the observables are the convolution algebra of the fundamental group of a mapping space from the surface that carries flux into the classifying space. Here, the classifying space is a standard one, but I just indicated that we actually will be taking the freedom, or we'll be generalizing, we will be looking at situations where this might not be the standard classifying space. We'll just be using the same formula, pi1 of maps into it. Okay, so this is a little effect from this article that I mentioned, quantum observables of quantized fluxes. The topological quantum observables on electromagnetic flux, or actually any Young-Mills flux, it's just in the non-abelian case, this is not actually the reduced phase space. So, but anyway, in the abelian case, it's just pi1 of the mapping space to the classifying space. Let's look at an example. What does this predict? Now, let's look at an actual surface here. So let's look at the unique up to iso-orientable surfaces, or maybe even oriented surfaces of genus G. And as you know, they're given by these presentations where for G equals 0, we have the sphere understood here as the square, all those sides identified with the base point. For the torus, of course, you know, there's this identification as a square where opposite side identified, and this is all the base point. And it keeps going this way. The two-hole torus, or the breadth, or whatever you want to call it, is presented in such a form where the same colored edges are identified. And there's a presentation like this for all genus G surfaces. And let's go here back. So what does our little theorem say in this case? What is the quantum observables through such a surface? This is a slightly hypothetical case now, even though I started with physics motivation, because it's actually non-trivial, even though textbooks like to talk about this case. Really non-trivial to say what it means in the laboratory to put flux through, say, a two-hole torus. This is because usually your things you have in the lab want to be like genus 0. So it's really hard. So that we can talk about this, but for a second we can just behave as theoretical physicists do and just ask the question. You can certainly think about spacetimes that have this topology, and that's what we're doing here. So, well, then what are we doing? We just saw we're looking at pi1. I mean, actually, I'm rewriting it again in this form. Pi0 maps into u1, but u1 itself is the circle, and the circle has all its motor groups concentrated in degree 1. So the circle is actually an Eilenberg-McLean space. It's actually the KZ1. So this circle actually classifies ordinary integral cohomology in degree 1. So that's why I'm leaving the pi0 here. This mapping space, its connected components actually the integral cohomology group of our surface. But then it's a standard fact from the easiest ways to use cellular cohomology from the way that these things were built from just these edges. Well, this is just a one copy. This is just the free abelian group on the 2G generators, so these 2Gs are just the 2G edges that appeared on the previous picture. They kind of generate this group, these colorful edges here. So that is what standard electromagnetism kind of, with Dirac charge quantization, with the standard quantization law, which is a choice. It's a canonical choice. It's a choice of global completion of a field predicts should be observables for such a surface. And now the interesting thing is that this is not observed at very low temperature. So these things called fractional quantum Hall systems, let me just show this whole slide here. So, of course, I'm glossing over a bunch of fine print here or details, but this is the upshot of the story. At very low temperature, experiments suggest, so what I'm really summarizing here is that you lower the temperature to see the material with this strong magnetic field through it, obtain this what's called the fractional quantum Hall state. And then there's arguments which I'm not showing here at the moment, that the effective field theory then of its effective particles are actually described by Chern-Simons theory. And so what I'm really showing now is what is the observables of abelian Chern-Simons theory as opposed to actual abelian electromagnetism on such a surface. And the interesting point is here, maybe I should have boxed this. The interesting point is that the prediction is that the group of the algebra of observables is not actually the group convolution algebra of Z to the 2G, but it's a set non-abelian, but central extensions of it, which is the hat, an extension by a copy of Z, known as the, do I say it here, as the integer, yeah, it's the integer Heisenberg extension. So let's look at what integer Heisenberg extension is. It's here. So it's that group here, which with underlying set is 2 copies of Z to the G. This is the naive thing we expected. There's one more copy, this spurious central factor. Elements are called N here, and the group operation of the sign of the dot here is like the naive one where you just add. It's just a group operation here. You add. You also just add here, but then this gets corrected by a co-cycle. So this is a formula for the semi-direct product of a certain co-cycle that carries here, and it's the Heisenberg co-cycle, and that you take, if we were multiplying A and B, you take this kind of skew combination of the A's and B's, they modify this N here. So if the Z's were R's, and this were also an R, this would be exactly what's called the Heisenberg group, and now it's called the integer Heisenberg group. And interestingly, as integrally, this cocycle is actually twice the unit cocycle. So if you compute X of this group with coefficients in Z, you find that this thing is actually element 2. This is already actually a cocycle integrally, and this is 1. But I mean, that's why it says here twice the unit central extension. In any case, this is kind of important when you want to compare this proof to the literature. It's important that there's a number 2. So it's that group that is kind of actually expected with a quantum correction, right? So then the question is, we should ask, well, okay, so it seems that in some way or other, so namely in the sense that if and when this Chern-Simons effective field theory description applies, whatever that means, the statement is just, you're no longer actually seeing Dirac charge quantization. You're seeing something that looks like an electromagnetic field, but it no longer has this classifying space, because we proved the theorem that classifying space does not predict the integer Heisenberg group at this point. So we can ask now, well, is there another flux quantization law? Is there another classifying space we can put here such that things work? So there's different ways to arrive at this, but let me just throw the following at you. So you might ask, well, how did you come up with this? I can maybe say later more about this, but let's just play around with it. Since we formulated the problem in algebraic topology, we can now just play with algebraic topology and see what things are predicted. Now we're making use of this fact that I mentioned before, that this classifying space BU1, remember this is our B2Z, this is our ordinary Dirac classifying space. One way of realizing it, it's homotopy type, is the infinite complex projective space. But that, of course, is the union of all the finite dimensional complex projective space whose first cell is, of course, CP1, also known as the two-sphere. If we forget, its other structure it carries. And so what I'm going to do now is I say, well, let's just try what happens if instead of CP infinity, we put S2 as the classifying space. And remarkably, and I'm talking a bit about how this comes about, which maybe need not concern us here, but remarkably, this statement is that produces exactly our integer Heisenberg group. If instead here, remember this is our observables, if we took the convolution algebra of this, it becomes our algebra of observables. Ivanov maps from our surface into the classifying space. And I've replaced this now with S2. And I'm indicating here how this comes about. The surface itself sits in some famous cofiber sequence. You essentially home that cofiber sequence into S2. You need to think about how it truncates. It does truncate. Then our Z2G appears here in a way that really identifies it as the previous elements generated by our basic cycles. And the interesting aspect is that the central extension here comes from the fact that it's an unstable effect. This is kind of curious here. So here our Heisenberg group appears, but we can see more. We can see where did the central extension come from. You see we're looking at pi1 of maps from S2 to S2. But that is the same thing as by some standard law by Cartesian or non-Cartesian. So first of all, you observe that this is actually, you can compute this mapping space equivalently in pointed maps because pi0 is S2 is connected. You can look at pointed maps here. Pointed topological spaces are closed monoid with respect to the smash product. Computing pi1 is the same thing as computing pi0 of smashing with a circle. And to do that, you're actually looking at the mapping space pi0 of the mapping space from S3 to S2. And now famously, so this is computing pi1 of pi3 of S2. And famously, this is actually into the integers whose generator is thereby identified with the Hopf vibration. This is a non-stable effect. This is something that goes away if we weren't looking at a low-dimensional sphere here. In that the stable homotopy group pi3 of S2 is of course just Z mod 2. So this is just to indicate how choosing a smaller classifying space can bring in more richer effect because it has what's called unstable consequences. Anyway, the Heisenberg group appears here, and so we're well. Okay, so let's see how are we doing with time. I have what 15,
20 minutes.
Okay, no, I want to come to the group point. So I have more. One can go further now and say, well, is this maybe just a coincidence? I mean, we just compared one group here, right? Is it maybe an integer family of groups? One can see more. One can see this. This actually knows about the braiding that people expect to see. The annuals actually come in. So there's good arguments that this S2, or not just good arguments. It turns out this S2 knows essentially everything. Knows everything that a bidirectional symmetry is thought to know in its observables. And let me come to the group points. In fact, here's more. So anybody who's actually seen Chern-Simons should have complained about what I've been doing because I actually swept under the rug the important parameter that Chern-Simons theory has. It's what's called its level. So it turns out, in fact, the statement is more refined. One can look on the top left there. So when I wrote pi1 on the previous page, implicitly, as one does, I was referring to pi1. You know, pi1 depends on a base point. And in just writing pi1, we mean the canonical base point. But in fact, the mapping space is non-connected. It has many components. In fact, it has Z worth of components. Maps from a surface to a sphere by what's called the Hopf degree theorem are classified by what's called the Hopf winding number. It's an integer. It's always when you map an n-dimensional closed manifold into an n-sphere, there's an integer worth of such maps. And so we have actually, for each integer, we can form a pi1. We can form pi1 in the connected components of winding number k. And it turns out all of these pi1s are all Heisenberg groups, but the extension is in general not by the free group, but by the finite cyclic group, Z 2 times the absolute value of k. There's just I have the citation cited somewhere here. This follows from old results by Hansen and Lamour and Thomas, who worked these out for completely different reasons in the 1970s. So this is an interesting aspect of this this game of flux quantization. It turns out very, very deep answers for physics, since one is just looking at mapping spaces into often low-dimensional topological spaces. These things were the topic of algebraic topologists in the far past. Actually, these days, topologists don't consider such mundane questions anymore. It's not an infinity category computation. This is just algebra. Anyway, so it comes out like this. It's the same formula, except that I put square brackets around all the n's. So all the integers are now modulo 2k. And this is really curious because remember, these are all observables. So the states are to be representations of these observables, right? The states are to have an action of the group algebra, which really just means that the representations of this group. But the irreps of these Heisenberg groups, they're exactly of this form. They have generators WA and WB. So I'm showing this on the torus now. For one of the two homology cycles and the other one. And they have the central generator, zeta here, or whatever it's called. And if you just unwind these formulas, it just means exactly this. If you pass WA past WB, it picks up this phase, Z2. It's 2. this too is important. This is reflecting, these are really two contributions here. Well, it's important for the fine print. It's not important for the general story. Zeta itself is just a cyclic variable, and it's in the center. That's what the last line means. It commutes with everything else. And it's exactly these relations we open textbooks. So these are Tong's lectures here on fractional quantum Hall systems. If you open lectures or any other textbooks on Chern-Simons theory of fractional quantum Hall systems, they will exactly show you this as the observable algebras of the fractional quantum Hall system for Chern-Simons theory at level K. So this K is thereby the sector in which we were here is thereby identified as the level of the Chern-Simons theory. And the previous case was level 0, which is kind of a subtle case in the Lagrangian formulation, but it's kind of unified here. This formulation. So these irreps, as you can just, these are the standard irreps. They are dim K, which is exactly the ground state degeneracy of Chern-Simons theory of degree K on a torus. I'm just showing this here because this is kind of important. If you want to see these anions, you want to see that there's ground state degeneracy, that the Hilbert space of states to the epsilon is not one-dimensional. And now comes my upshot here for today. Oh, okay, we have 10 more minutes there. So there's now a very nice way of summing this all up. Let's zoom in here first, the left piece. So this is not a trivial consequence of what I just said, but let's maybe look at it to see that it is a good statement. So we see now that we can summarize the situation by saying that the quantum states, I'm not sure if I'm using my English grammar is good, at any level, I mean at all levels at once, unifying all levels, are unified in a single group point representation of the moduli. So I'm calling this the modular space here. It's a thing that classifies our fluxes, right? So we have this mapping space. I'm showing it here for the torus, just because that's what I introduced before. And I'm putting this pi1 here. Remember, that was the notation for passing to the fundamental group point. It's just to amplify the way. Looking at the space now is a fundamental group point. So by the fact that I called the skeleton theorem, this mapping space is the disjoint union, or pi1 of it is the homotopy equivalent to the disjoint union over all the connected components, which are all the Ks. Right, maybe I should write this in board. Let's write this in board. About to say here. So I didn't, maybe I'll put this on the slide. You see the slide is a little bit unfinished, but in fact, it should say the following now. So we saw that for a general group point, that representations are just maps to group point maps to the core of complex vector spaces. But it also means that the representations up to equivalence of representations are actually equivalent under homotopy equivalence of group points, which you can just pre-compose with these things. So now we saw that pi1 of our mapping space, with G here maybe as 2, is actually by the skeleton theorem. That's just my name. There's nothing to call. It's called every group point is equivalent to its skeleton. It's the disjoint union over the connected components of this guy, but we saw that these are the levels, K and Z, of the looking group points of pi1 of the corresponding things. But this is not just pi1 of the mapping space sigma 2G, S2 at K in the connected component. So I'm saying, where am I forming the pi1? So that means that the group point representations of this are now just products of all K of the ordinary group representations of these pi1. But these were just our observable algebras, remember? The representation of this was just our states. The irreps of these groups were exactly these fractional quantum Hall states for each K. So it's in this sense that a single rep here, that this single rep, single group point rep unifies all let's say CS states, state spaces for K, for all levels K. So in this way, the level becomes kind of a part of the physical system. You can choose where you are. Okay. And thereby now we have, these states fit very neatly into this general framework of, so we want to, next tomorrow, I want to now be talking about what does it now mean to measure these things. But maybe if I have 5 more minutes left, let's just look at the right side of this slide here. This is what I'm going to use tomorrow. So I've actually, if we're really looking at Chern-Simons theory here, something that is not so obvious when you think of this in solid state physics, but when you're really looking at this as Chern-Simons theory, then you want to be, when Chern-Simons theory is being topological, it is what in physics is called diffeomorphic or generally covariant. So the thing you actually want to be looking at is not just the plane modular space, but its homotopy quotient by diffeomorphisms. You want to say that any two configurations that differ by putting them back with a diffeomorphism are actually the same, because this is supposed to be a diffeomorphism in general theory. So what we can actually form is the homotopy quotient of our modular space by the diffeomorphism. I'm putting the plus here for conventional reasons. It's the orientation preserving diffeomorphism, since we made use of the fact that
Should this be sigma G or are you fixing the genus?
oh yeah, that's another typo. Yeah, I wanted G here. Yeah, okay. I hope I remember all these titles. I'll fix them in 10 minutes.
I can also look over that afterwards.
Yeah. Good for you. Yeah. Either it should be, but I do want to be talking about all G's here. Yeah. And so this is going to be important tomorrow. These diffeomorphism. Well, okay. So this is if we're really being serious about Chern-Simons theory as being a topological field theory, then this is the actual. So you see, this brings us more actions, because now diffeomorphisms, in addition to what's already acting, kind of the maps here were kind of gauge transformations or topological shadows of gauge transformations between the actual gauge field. And now this kind of brings in addition the gauge transformation of the field of gravity, if you will, even though it's topological, but there's still a difference. So we can make this precise. You can work this out using the fact that the diffeomorphism group of a surface is essentially, it has no higher homotopy groups, except for a subtlety actually for the torus, which is maybe why I changed my mind in between typing this formula here. But anyway, so the statement is that subtlety for the torus that the pi1 of this homotopy quotient is actually the quotient of the previous pi1. And there's another typo. I should have ignore this line. There's a pi0 happening here. Yeah, I just typed this a few minutes ago, actually. Anyway, it turns out, okay, maybe I'll start over again tomorrow at this point and clean this up. But it turns out the groups in here are the previous pi1s, a semi-direct product with the mapping class groups, namely pi0 of these diffeomorphism groups. And this is, of course, exactly what traditionally is known to act also on these state spaces of Chern-Simons theory. Mapping class groups of these surfaces, which for this simple case, oriental genus G surfaces is just the symplectic group with integer coefficients on Z to the 2G. In particular, for G equals 1, this equivalent to SL2Z, the standard modular group. And so this shows that there's another group acting on all our states, also included now in the group point representation. If you think of all the states being these group points representation, it knows about the gauge transformation, the gauge field, and this gravitational effect. And the plan for next time is, which is tomorrow, just in a few hours, that we look at richer surfaces here, and we surfaces with boundaries and punctures. And then we see the mapping class groups become quite rich. They know about this braiding that one wants to see in topological quantum computing, coming from the fact that the punctures may move around each other. And they know about what does and does not happen at the boundary, which is important, I think, for actually implementing these things in a laboratory, where you can't actually expect that if this is really playing the role of a gauge diffeomorphism group in the bulk, then you can't actually expect that you can control these operations, right? So this, maybe I close with this comment. So we see here in these group point representations that we've equipped our quantum states, as I said, with operator actions. But these operator actions come in two different kinds. There's symmetries, acting, where you just say this is just everything is just symmetric under something, but also actual physical evolution, like Schrödinger evolution, is of course also given by a group action. So these group actions come in conceptually in two different flavors. Some of them should be regarded as symmetries, some of them should be regarded as being actual physical transformations. And so next we want to maybe disentangle which is which to see what's maybe really going on in a lab. But I'll stop here.